lead-acid battery. So lead-acid battery is probably the oldest types of battery to know, and is nowadays, even if it's so old, is still attractive for a lot of different applications, for instance in vehicles. Basically we can say that the lead-acid batteries is batteries composed as sponge of lead, as metallic lead, and lead peroxide, respectively on the negative pole and on the positive pole as electrode. Basically, one of the main important characteristics of this device is the weight. It is really important. So lead-acid battery is a real heavy battery, and for the reason it cannot be used for application in the case of smartphone, in which a huge, or watches, in which a huge energetic density is important and necessary. Because lead-acid batteries are characterized with a quite pure energetic density and specific energy. What does it mean? That literally, even if we can store a certain amount of energy, since the weight and the volumes is so important, the ratio energy versus weight and the ratio energy versus volume is significantly small, and so the energetic density and the specific energy is reduced. But from the other hand, even if we have this interesting problem concerning the use of these batteries, these limitations, is even true at the same time that lead-acid batteries are able to provide high source current, so we can provide a huge current during the use, and this is still remain one of the more important aspects concerning this battery, for instance, for use in vehicles. We need to remember that for start a vehicle's motor, we need at least to have 4 ampere as a current. And so it's important to have something that can provide this current value. And well, lead-acid batteries can do that, because even if it's true that the specific energy is quite pure, we have a relatively high specific power. So this relatively high specific power, connected with even with the huge stability, the possibility to recharge these types of device for a lot of times, so we have a huge important rechargeability of these secondary batteries, and also the reduced cost, so we are speaking about cheap materials, make this lead-acid extremely interesting for application even nowadays. So I have described basically the main important aspect, the negative aspect, so the pure and bad specific energy, but also the positive aspect, so the high specific power necessary to run a significantly high source current, and for this reason allow to start a motor. Maybe we have low cost, so, and we have also a high stability. And rechargeability. So, even if we have this important problem concerning the pure specific energy due to the important weight, we have even a lot of interesting aspects. So, from a practical point of view, which are the components of a lead-acid battery? So, the components of a lead-acid batteries are always, as in each single battery, a negative pole that during the discharge is acting as the anode, yes, an electrolyte, the positive electrode acting as a cathode, and the external circuit. So we can say that the anode, so the negative pole, the negative electrode during discharge, is made of metallic lead, a sponge, metallic lead in sponge form, sponge metallic lead, whereas the positive one is composed of lead peroxide. So this quite fragile black powder created due to electrodepositions of salt of lead in the industry for the creations of these electrodes. So basically we have here lead peroxide and your sponge of metallic lead. So what is important to say that at the very beginning, when we are at full load, so when the battery is completely charged, we have this electrode. This is completely made of lead in oxidation state 0 and lead in oxidation state +4. Here we have the resistance. We have a separator. It could be a separator composed of different types of matter. And we have inside an electrolyte. And this electrolyte is an acid water solution of sulfuric acid. So we have sulfuric acid in water. And in particular, it's important to say that the concentrations of the sulfuric acid in water is around 40%. So more precisely, 41% of sulfuric acid in water. So a ratio between water and sulfuric acid, it is between 3 versus 1. So water, 3 parts of water and 1 part of sulfuric acid at least. So basically, this is the main structure. And if we want to look at the similar reaction of discharging, on the negative pole we have the oxidation. So we have the interactions between this and the anion of the sulfuric acid with the release of, with the formation of lead sulfate and 2 electrons. So we are passing from this having 0 as oxidation number to this one having +2. So this is a real oxidation. When we are creating these types of solid, basically we are promoting the oxidation. So it's important that due to a product of the oxidation and the release of electrons that can reach the cathode in a further moment, we have as a product of these oxidations the formations of these insoluble or purely soluble salts. We will see also the solubility constant in a moment. So this is a quite pure soluble salt, and we can have the deposition of these species on the surface of this electrode. So maybe depositions of this lead sulfate here. And this is the reason for which if you are using this battery for a lot of time, we can create more and more oxidations product, more and more lead sulfate. And when we are covering completely the surface of this electrode, we are not able anymore to ensure the opposite reaction during our rechargings, and the batteries just simply will die. So we need to be aware to avoid a complete total covering of the electrode due to the formations of this product. So it's important to avoid an excessive discharging process. This for what concerns the negative pole, but we have also the positive one, in which again we have the formation of lead sulfate, but in this case starting from lead peroxide reacting with again this anion plus 4 times H plus and the 2 electrons. And this leads to the formations of the corresponding lead sulfate and water. So what is interesting is that we are consuming sulfuric acid when the reaction is proceeding in order to promote the formations of clean water. So the water content increase with respect to the sulfuric acid content that decrease due to the development of the reaction. And also in this case, the product of the reaction is still remain this purely soluble salt. But in this case, since we know that this is +2, but we have started from +4, this reaction is basically a reduction. So the same product is created, but this is created toward an oxidation, and this with the generations of a reduction. But we have the same problem concerning the formations of this species, that obviously this is a rechargeable batteries. So this is a secondary batteries. We can apply a potential difference in order to ensure the opposite reactions, promoting the flowing of electron in this direction. Since we know that in this condition, for instance, the potential of this semi-reaction is around minus 0.36 volts, and the potential of this reaction is around 1.69 volt, with a total potentials difference, with a total d.d.p of the battery in open circuit conditions that is higher or close with respect to volts. So quite high power basically. And the point is that if we want to ensure the opposite reaction, we need to increase this potential with respect to this one, and so ensure basically the realization of the oxidation of the reductions of this species and the oxidations of this species. So transform the negative pole in a cathode and the positive pole is an anode, as we well know. But obviously, in order to do this, we need to provide a certain d.d.p with an external potentiometer, and this d.d.p will be higher than 2 volts. But we need to be aware to do not overcome the value of 2.4. Why? Because if we increase too much the voltage, if we increase the voltage in order to promote the recharging over 2.4 volts, we can promote the formations of hydrogen and oxygen due to the electrolysis of water. We will see a specific lesson dedicated on the electrolysis of water, and actually the electrolysis of water from a thermodynamics point of view is promoted even at lower voltage, even at voltages that are higher than 1.23, for instance, 1.26. But obviously, for cynetics point of view, in this case, we can appreciate the electrolysis of water with the creations of oxygen and molecular hydrogen from water dissociation only when we are increasing the voltage on a value that is up to this one. So we need to be aware to do not overcome these types of value when we want to recharge our battery. This is an important hazard, and we need to take in consider about that. So basically we have this reaction, this oxidation, and we have this reduction. This is important to say that basically the role, in this case, of the sulfuric acid is not only in lead-acid battery to act as electrolyte and close the circuit, but basically the presence of the sulfuric acid with respect just simply water is also responsible for an increase in the final d.d.p, because the final d.d.p is around 2 volts. And so this means that if for each single cell we have a theoretical d.d.p of 2 volts without considering the overtension, and that means that we can collect maybe 6 different types of cell in series in a stack. We can obtain a bigger battery having a total power around, a total output voltage around 12 volts. This is what often is done in order to create a battery used, for instance, for start vehicles. We are using a stack composed of 6 different types of cell, and so 6 per 2, it means that we have a total output voltage equal to 12 volts. But for us to consider the single cell, this voltage is 2 volts. It's basically the difference between this reductions potential associated with these semi-reactions of oxidation and this reduction potential associated with this semi-reaction of reduction. But it's important to clarify that if we are eliminating, for instance, the contribute due to the sulfuric acid, this d.d.p, it will be extremely lower. And so the role of the sulfuric acid is not only to close the circuit, but modify the thermodynamics of the process in order to increase the final output voltage. In which way we can demonstrate this? We can demonstrate this just looking at the way in which the Nernst equations are modified if these Nernst equations are associated with a certain semi-reactions containing sulfuric acids or not. So let's describe here basically what is important, what is important concept from a thermodynamics point of view. So look at the Nernst equation. So we have, we have here our semi-reaction. Okay, let's start. Let's imagine to consider the semi-reaction of a lead-acid battery in a real situation. So the real semi-reaction during dischargings are respectively what we have previously described. So lead present in the negative pole as sponge metallic lead, 0 as oxidation state, plus this anion release through dissociations of the sulfuric acid, the oxidations that lead to the formations of this purely soluble salt, and the release of 2 electrons. Then we have the reduction, so the reaction between the lead peroxide plus the same species plus 4 times H+, leading to the formation of the same product and 2 times water. And so this means that the total reaction is this one, plus this one, plus this, and 2 times this, and 4 times this means 2 times literally sulfuric acid. Obviously electrons, here we have also the 2 electrons that are eliminated, since we have electrons both here and here. 2 times lead sulfate and water. This is the total overall reaction, in the case in which sulfuric acid is used as electrolyte, obviously in a percentage, 30% in water. So these obviously 2 semi-reactions are associated with a specific Nernst equation in order to describe the total potential as a function of the difference between this reduction potential and this one. In this case, the reduction potential we know is minus 0.36 volts, and in this case is 1.69 volts, and so the difference in d.d.p is around 2 volts. But what's happening if we are imagining to run the same reaction avoiding the presence of sulfuric acid? So we are imagining to proceed the same reactions but without the presence of sulfuric acid. So what is happening is that this reaction is now transformed in another one. It's not anymore the reactions that we have described before, but is this reaction. 2 plus 2 electrons. And this reaction is not associated anymore with this reduction potential, but with an higher one, minus 0.13 volt, with respect to 0.3 minus 0.36. So it's higher, it's less negative. And then the same obviously for what concerns the positive terminal, in which, since we have the presence of sulfuric acid, we have only our lead peroxide plus 2 electrons plus 4H+. That gives, again, lead 2 plus and 2 times water. And this reaction is associated with a potential, an open circuit potential, that is equal to 1.48. So we have a difference in this case that is smaller with respect to the difference before. Before we have minus 0.36 and 1.69, and so a final d.d.p around 2 connected with this reaction. But for what concerns this new reaction, the final d.d.p is smaller than 2, because this is higher and this is smaller, and so we are reducing the gap, and the difference it will be smaller. And so basically we can say that from a thermodynamics point of view, the rule of sulfuric acid is also to increase the final d.d.p. And from a Nernst point of view, what we can say is try to write down the nearest equation, for instance, associated with this reaction. So let's try the nearest equation associated with this reaction. We have our reduction potential in open circuit condition is a function of the same and standard condition plus RT logarithm and so we can collect all the constants parameter in a single constant known as K. We have here 2. Why 2? Because basically 2 is the ratio between the mole of electrons over a mole of substances. Here we have 2 electron exchanged for each mole of lead. Remember the dedicated lessons or nearest equation in order to understand this passage very well. So logarithmic, since we have already transformed the natural logarithmic in 1 base 10, so I'm just simplifying the computings in order to speed up the demonstration. And here we have also basically the activity of the reagent, since here since it's positive. And so we have this for this H plus at 4 and this 2 plus and the activity of water. Now we can consider that since this is a solid, it could be considered as pure, and water it could even be considered as pure, and so we can even eliminate these 2 terms and remain with the activity of H plus over 4 on the activity of this one. And so we have these nearest equations that solve with the introductions of the specific parameters allow us to obtain this value or something that is close to this value. This value, since we are looking for this reaction, but it's basically the same also for the other reaction, this reaction. So now what is happening if that we are imagining to introduce sulfuric acid? Okay, this is the nearest equation associated with this reduction if no sulfuric acid is present. But we know that the real lead acid batteries involve sulfuric acid. And we know that their same reactions with the introduction of sulfuric acid is different and lead to a reduction potential that is higher, 1.69 we respect this one. How this concept can be expressed with the use of nearest equation? Well, we know that if we are introducing sulfuric acid, we can appreciate the formation of, as a product, not lead 2 plus as lead 2 plus, but lead 2 plus as lead sulfate. This pure soluble salt in an equilibrium of dissociation that is lead 2 plus and this anion, sulfate anion. Obviously, since this is a really pure soluble salt, the solubility constant is really small and is equal to around 1.8 per 10 elevated to the minus 8. What does it mean? That the solubility is extremely low. This equilibrium is shifted a lot here. And we know that the solubility constant is equal to the product of the concentration of these 2 species in the dissociated state. Or better, if we want to be more precise, is the product between the activity of these 2 species. And this product is very low since this system is shifted a lot here because the solubility is reduced, and this is also the reason for which we have the problem of lead sulfate sedimentation that can kill the batteries if we are discharging this a lot. So basically we have this situation, and what's happened is that taking advantage of this, we know now that the activity of lead 2 plus is equal to the solubility constant over the activity of this anion, the sulfate. And so we can substitute this one here. And so this is not anymore this, but is Ks. And here we are multiplying for the activity of this anion. So we are changing the Nernst equation with the introductions of these terms inside the Nernst equations of this reaction. The reaction in which the sulfate is not already present. So the Nernst equation at the very beginning, it was the Nernst equation associated with this type of reaction. Since now we have made this trick, we are passing on a Nernst equation that is describing this semi-reaction. So basically now what is important to say is that we can take this component and put it outside. So E is equal to E0 plus K2 log of because this is at the denominator, log of Kx plus this activity of this. And since this value is extremely low, is 1.8 per 10 elevated with minus 8, this type of result, it will be negative, and since we have a minus sign before, we have a negative for something that is negative, and so this becomes positive. And this means that we are taking this and we are summing this for a positive contribute. What does it mean? That the total open circuit potential, it will be higher, because we are summing this for a more positive term with respect to the starting situation. And so, also from the Nernst thermodynamics point of view, we have demonstrated in which way, basically, by introducing sulfuric acid, we are increasing this potential. If we can do the same things for what concerns this, so let's define the Nernst equations of these reactions and later substitute with the solubility product this parameter in order to describe the Nernst equations of the corresponding situations with the introduction of sulfuric acid, where if in this case the total potential or in open circuit conditions increase, in this case decrease. And so the gap between the two reactions is increased, and so the final d.d.p is higher if we are introducing sulfuric acids in our electrolyte.